Hello everyone, welcome again to my SAS tutorials. This is lesson 10. Today I'm going to be talking about proc_core for calculating correlation coefficients. And I'm going to be showing you an example out of the SAS help manual that shows you how to calculate 4 different measures of association. To get to this example, you just hit F1 to get into the help and documentation manual, and you're going to want to click on search, type in core, C-O-R-R, and if you scroll down you can see this core procedure examples of core procedure. When you click on that, you'll have a nice table of contents here, and the first example here, computing 4 measures of association, is the example that I'm going to be showing you today. So if you copy the code that's given to you in this example, you won't be able to run it until you actually copy in the data set as well. So to get the data set, you would just click on this link right here, getting started core procedure, and it's going to give you here this data set on physical fitness, where they looked at men in some physical fitness course at North Carolina, and they measured their age, weight, their time to run 1.5 miles in minutes, and the amount of oxygen they used. So if you just copy the data set there, you can paste it into SAS and run it, and then you'll have the data set needed to use this example. So here's the data set as I've copied it into SAS. There's one thing I want to point out real quick, which is this @ symbol here on the input statement. If you ever see this @ basically what you should know is that it's telling SAS after every 4 data points to continue reading in data points in the same line. So for example, here you can see that there's one set of 4 data points here, and then another set here, even though they're on the same line. So when they're on the same line like this, this @ tells it to ignore the points as they're, or sorry, to read in the points as if they were on different lines. So this becomes the second observation, this is the third observation, this is the fourth, and so forth. And if we wanted to show that, all we'd have to do is do a proc print on the fitness data set and run that. And you can see here that, if I zoom in for you, that the first observation is that 44 and the second is the 40, not the other 44, which would have been the case if it had read this first and then this. But because we have that @ it goes ahead and reads the second observation even though it's on the same line. So that's just one little caveat. Let's get into correlation. The simplest way to do any kind of correlation procedure in SAS is simply to type proc_core, specify the data set you're working on, and then which variables you want to see a correlation between. So if we wanted to see between weight and runtime and ran this, we would be able to see a Pearson's correlation coefficient for the weight and runtime part. Let me zoom in here for you again. Now the Pearson correlation coefficient is the only parametric correlation coefficient that I'll be showing you today, and with almost every correlation coefficient, they're going to give you some kind of p-value, in this case right here, that tests the null hypothesis that there is no association, or there is no correlation, or there is no relationship between whatever variables are being compared. So here it's comparing the runtime in this column, in this column, with the weight in this row. And then there's this weight column and this runtime row. So every correlation coefficient table is always going to be some kind of matrix like this. Here it's a 2x2 matrix because we have 2 variables that we're comparing. Every time one variable is matched up with itself, it's going to have a perfect correlation because every value is itself the same value. And at the very bottom here, it shows you the number of observations. So in this case, between weight and runtime, there's a Pearson correlation coefficient of about 0.2. But you can see that the p-value is not significant. So we cannot refute the null hypothesis that there is no association. So between weight and runtime, there might not be really a correlation. Now the example provided by SAS is actually a little bit more in depth. It gives you 4 different measures of association. And if you copy it, here's the code for it. Again, you can see this proc_core and on the data set, and it's going to give you the 3 variables it's going to assess are weight, oxygen, and runtime. And it has a little bit more going on here. you can see that it's going to do some kind of ODS graphics because it has ODS graphics on and ODS graphics off on the top and bottom, but that's because it's going to give you this matrix plot with histograms, and I'll show you that in a second. The four measures we're going to look at here are the Pearson correlation coefficient, Spearman correlation coefficient, Kendall's tau, and Houghton's test of independence. Now when we run all of this code, if we had not specified Pearson coefficient here, it would not have been provided by default. But if you don't specify any of these, only Pearson's is provided by default. So just keep that in mind. If that you want to have a Spearman's correlation coefficient as well, then you want also the Pearson's because it's given usually by default, then you have to specify it again. Now the thing that you have to understand about Pearson's correlation coefficient is that it's parametric, but all of these other examples are non-parametric. And if you remember from last time, parametric and non-parametric tests basically have that assumption that the data comes from a normally distributed data set. With correlation coefficients, the other thing you need to know is that they only work in this case on continuous data. So the points of data have to be, they have to be continuous. They can't be categorical. And the last thing you need to know is that these coefficients, these non-parametric correlation coefficients, are calculated in different ways. Whereas the Pearson correlation coefficient uses the actual data points from your data set, the Spearman's correlation coefficient looks at the ranks of variable data, the data of your variables in your data set. So it will rank, let's say, the highest value at number 1, and then it will go all the way to the bottom at number, let's say, 31 or whatever. The Kendall's tau, it uses something called concordant and discordant pairs. What does that mean? A concordant pair basically says that if one point precedes the next, or is below the next, then it's concordant because they're going in the same direction. A discordant would be one point going one direction and then the other point going in opposite direction. And then Houghton's measure of independence, I'm not going to go into it too much, but just so you should know that the Houghton's measure of independence is like the Kendall's tau test in the sense that they're measuring dependence or non-dependence. So let's run this code and see what comes out. Now if you look at the results tree here, you can see that there's 1, 2, 3, 4, 5, 6, 7 different items, and pretty much the first two are always going to be there. The variable information, which tells you which variables are going to be assessed here, and then you're going to have some simple statistics with the mean, median, minimum, maximum, standard deviation, etc. Now because we specified Pearson first, the Pearson's correlation coefficient is going to be provided here, and if we had not specified any of the other tests, this would have been provided by default. You can see here that between weight and oxygen, there is a negative 0.15 correlation coefficient. That means that as weight goes up, oxygen goes down, and vice versa. As oxygen goes up, weight goes down. Here we see that for weight and runtime, there is a positive correlation coefficient, meaning that as weight goes up, so does runtime. And this kind of makes sense if you think about it. Now, below those two correlation coefficients is the p-value. In this case, both of them are non-significant. So we can't really refute the null hypothesis that says that there is no association. In other words, we cannot make a definitive conclusion that there is an association. However, this this p-value here, less than 0.0001, is highly statistically significant, and that's between oxygen and runtime. Now, if you ask yourself, okay, well, this is a statistically significant p-value, what does that mean? It means that we can refute the null hypothesis that there is no association and go with the alternative that says there is. And in this case, the alternative says that there is a association between runtime and oxygen that is a negative correlation. There is a negative or inverse relationship between these two. As you have more oxygen, your runtime goes down, and that kind of makes sense if you think about it. Now the Spearman's correlation coefficient is below, and it's going to have basically the same conclusions. Here you can see that there's that same negative weight and oxygen relationship, but it's not significant, and the same weight and runtime positive association, but it's also not significant. And then oxygen and runtime, we get that same significant inverse relationship. Remember that the Spearman's correlation coefficient is based on the ranks, not on the actual data set. So it's a non-parametric version of the Pearson's correlation coefficient. Now the last two are the two measures of dependence or independence. So Kendall's tau b is also given in this kind of correlation sense, where a 1 represents perfect positive relationship and a negative 1 represents a perfect inverse relationship, and a 0 represents no association or no dependence. So in this case, we can see that the same conclusion, if I zoom in here for you, the same association between oxygen and runtime is observed where it's a negative relationship that's also significant. Lastly is Houghton's dependence test, or a test of independence. Now this one is a little bit trickier. Without going into too much detail, I would actually point you to the Wikipedia article for it if you want to get some of the theory that's going on. But the idea is that you're testing for independence and you want to see whether or not they're independent of each other. And in this case, we can see that oxygen and runtime show that they are independent. Actually, let me clarify that. Houghton's measure of dependence, non-parametric measure of association that detects general departures from independence. Make sure that it varies between -0.5 and 1, with 1 indicating complete dependence, and 0.5 I'm guessing complete non-dependence, and the null hypothesis is that the D is 0, indicating complete independence. So that one's a little bit trickier for me, only because I've never actually been taught it. I'm just going off of what's provided here in the SAS help manual. But if you've been taught it, you probably know better than I do anyway. One last thing I want to show you is this matrix plot with the histogram option here. If we click on the item in the tree, we can see that this is what the picture looks like. So here we can see that between weight and oxygen, remember that it was not a significant relationship, and you can see here that the points don't really seem to fall in any specific direction. But we can kind of see that it goes downwards like this. So that's why we saw that negative correlation coefficient, because the points tend to fall along this diagonal. Whereas for runtime and weight, they're falling along this diagonal, and so we can conclude that there's a positive association, but again, it wasn't a significant finding, and you can see that the points are all over the place, and that's why. But between runtime and oxygen, they're now starting to fall along a line. They're starting to fall along that same diagonal, and here they're going diagonally in this direction, and that way you can see it's a negative correlation. When you specify that histogram in parentheses here, it gives you these 1, 2, 3 histograms here. If you had not specified that, if you took that out and ran the same code, it would have just given you the name in each of these cells. And it's not as pretty, I guess, and it's not as useful to just have that name in there. But if you were to try to publish this, or if you were putting this into a PowerPoint of some sort, you might want to put it this way, and to do that, all you'd have to do is take out that parentheses histogram. Personally, I like it the other way, but it's up to you how you want to do it and how you want to present it. So that's pretty much it. Proc Core is really simple. Tune in next time, and we'll go over some